Of course, those are most challenging because everybody knows everybody, and then you have no guilt in shaming your speaker by asking tricky questions. So I'm expecting a lot of those. And also, I think I reported some of the progress in this paper several years ago, but it took a lot of time. So we have 4 collaborators: Sergey Gukov, who spoke here last week, Satoshi Nawata, Dupay, and Ingmar Saberi. And yeah, essentially it's going to be a physics talk, but sort of some of the results are on the mathematical rigor, but most of them are not. And in a sense, it's an invitation for you to find some ways to continue those ideas to, and then, well, to more rigorous mathematical setup. Yeah, anyhow, I was physics postdoc back then, but anyhow. So let's begin. The quick review of modern view on quantization and quantum mechanics. So quantum mechanics, from the point of view of a mathematician, is a modern symplectic geometry, right? So if you have a well, harmonic oscillator, have a p squared plus over 2 plus x squared over 2, there's a kinetic energy and a potential energy. So there is this parabola over here. So you have, particle starts here with a maximal potential energy. It goes down, gains its maximal kinetic energy, its potential energy goes to 0, and then it cycles back and forth until you bore it, right? So, but you can make it more geometric by drawing the so-called phase space, right? So we have a symplectic manifold M with a symplectic form dp wedge dx, right? And where the energy level of this of the oscillator is a boundary of a certain disk, right? And then, oops. And then the Lagrangians here are some middle dimension manifolds such that the restriction of symplectic form on those on those Lagrangians vanishes. So in this example, the fact that the submanifold of Lagrangian is a bit degenerate because it's just one-dimensional example, but you can imagine many coupled oscillators and ask a question there. So the symplectic form is locally exact on those Lagrangians. So here Lagrangian will be like, example for Lagrangian is the boundary of this disk, right? And you can compute the Liouville form, which is the primitive of omega. So here, for example, it might not exist in say here or there, depending on which coordinate frame you choose, but anyhow, locally it's pdx or xdp or combination of thereof. Right, and then how do we quantize it, right? So the picture from quantum mechanics textbook, we have energy levels of those oscillators, right? You would compute the symplectic area, right? And then it will become integral in units of the Planck's constant. And so there's this, of course, factor of 1/2, which is very important, but roughly speaking, that's what's going on. So you either integrate over the disk or you integrate over the Lagrangian, and you integrate the primitive, right? So, and then moving further on, we have coordinates and momenta. They are promoted to the operators. Poisson brackets on the symplectic manifold become commutators. So in this case, P and X perform Heisenberg algebra, where X acts with a multiplication and P acts with a derivative, right? And then, oops. Yeah, and the Lagrangian constraint is upgraded to the operator, right? So that becomes a Schrödinger operator, holomorphic Schrödinger operator, and the which is an ordering differential equation. And in this case, it has square integrable solutions only for special values of the energy, right? And that leads us to the quantization conditions. And so the first one is the Gaussian, and then of course there are others. So in a sense, today you'll be doing similar calculations, only in a much more sophisticated context. So basically, how does this sort of quantization program work? So at least we hope for this program to work. So we have a symplectic manifold, M omega, manifold in the symplectic form. So that becomes the Hilbert space of your system. Algebra of functions becomes algebra of operators that acts on Hilbert space. And the Lagrangian submanifolds, which are described by some system of equations, they become states in the Hilbert space over here, right? So this is the standard program. At the moment, it's sort of a wish list, right? So it doesn't always work. Of course, in all kind of physics examples, it works because spaces are usually simple, something like Cn. But you can ask this question for any symplectic manifold with singularities and stuff, and of course, the answer is not known yet how to quantize it. But today's example, so I jump very quickly. How do I? Interesting. I should really click very fast. So in my story today, we'll have the algebra will be double affine Hecke algebra. The Hilbert space will be formed out of DAHA representations. And those states will be certain high state vectors, right, which we'll construct explicitly. So the Z will be certain polynomial or well, series, as we'll see. Y will be this one with Magdalene operators, right? And its weight, we'll be talking about which values this combination takes, and that will, describe different kinds of representations. And then dimensions of those modules will be dimensions of those representations. We'll be computing we'll compute them using what is called a model approach, right? So there will be some space of open strings which are stretched between different branes, and then there's a standard formula which allow us to compute that. Yes, question. Well, I mean that's the wish list, right? So eventually we wanted to make something like a factor. Yeah. Well, I mean, yeah, you need to specify what you mean by quantization, right? So there's a deformation quantization and the geometric quantization. Yeah. But you are deforming. It doesn't have to be isomorphic, right? So
yeah, but it's not it's not like you're looking for looking like for some maps to go to maps that's normal.
I see. Yeah, sort of the.
Well, now I appreciate why
it's
yeah.
Well, because sometimes we just we have to know what the answer would look like. Yeah, sort of. Yeah, but for today, what I mean by quantization in this talk will be something very special, with deformation quantization of some space. Okay. So yeah, we'll get talk about double affine Hecke algebras, a little bit of history. So this is a book by Ivan Cherednik. It's the title is double affine Hecke algebras. So DAHAs and some related algebras were introduced by Cherednik in the study of Magdalene polynomials from the point of view of representation theory. So he wanted to merge together combinatorics and representation theory. Then from the algebraic point of view, Alexei Oblomkov, he showed that in type A, which again will be part of today's story, DAHA is a deformation quantization. It's a flat one parameter deformation of Poisson structure on the so-called Calogero motor space, which I'll discuss in a second. And then the space can be understood as the SL2 character variety of a torus with a puncture, with a certain simple monodromy attached to the puncture. Yeah, and then basically the idea is to understand geometric constructions of DAHA representations by studying geometry of this space. So that's the plan for today. Some related developments, because people think about this from different directions. So there's been a long program by Kensevich and Soberman, which they call holomorphic Loy theory, which among other things addresses questions that I'll tell you about. But they have a very abstract approach. It only, as far as I understand, they don't have any explicit examples yet. In the sense, our story is a part of it would provide the first non-trivial example. So we'd study a category of holonomic D modules, and then which was sort of generalized the Fukaya category construction that we have.
By holomorphic Loy theory, they mean what? Loy theory of homomorphic factor?
Yeah, that's right. Yeah. But essentially, they want to introduce understand mathematically what BCC brane is, what all those not only Lagrangian branes but all other branes which appears in A model by studying some not only D modules with holomorphic support, with the holonomic support, but with all others. So that's what Jan told me. Then people who studied Pinlet equations, right? So it's a different group of people, a Japanese group and others. So they had the well, when you have this Pinlet family, you can have a bunch of singularities, and then as you study various degenerations, as I was told by O'Hara, that after I gave a talk there, he said that, well, we find similar singularities as we have, so that's interesting. Then so Fukai people like Edku Likili and Polishuk Likili and others, they've been studying certain Fukai categories of spaces which look similar to the flat connection, modular space of flat connections. And finally, more recently, there's this paper by Bezrukavnikov and Losiev who construct finite-dimensional modules of algebras that quantize Nakajima equivalent varieties. Right. Yeah, so I still need to understand this better. I don't know much about it. Okay, so let's begin, right? So any questions about introduction? So let G be a Lie algebra, and then the Hecke algebra is defined as a deformation of the group algebra of the Weil group G, right? So for, again, today we'll only be talking about SL2, so let me just give you the formula right away. So it's generated by capital T, and the relation is big T squared minus T minus little t times T plus little t inverse is equal to 0. So well, the little t is the parameter of deformation. And then affine Hecke algebra, or AHA, is defined as this quotient, right? So there's a polynomial algebra of capital X in inverse, capital T, this coefficient T, little t, and there are two relations, right? There's the braid relation. So here T is like T is all the braid generator, and then X is like a affine generator, and this Hecke relation. And then, oops. And DAHA is copy of two AHAs, right? As the name suggests. So we have AHA for X and T and AHA for Y and T, and you sort of introduce an additional parameter Q, right? And this is what the algebra looks like. So I will denote it with this H double dot of Z2, and Z2 is the Weil group for SL2, right? So it's this field of fractions tensored with C of X plus minus Y plus minus T divided by, well, Hecke relation, and then two braid relations for X and Y, and this relation that combines them together that looks like some kind of quantum torus relation.
Hecke algebra so T is like this generator of this.
Oh, the braid group. Oh, no, yeah, Y, that's right. Yes, so T comes from Weil group, yes, and like X and Y are two different. Well, so yeah, so so I'll give you the geometric explanation on the next slide. So here's what X is, right? So you take a torus, and you take the orbifold fundamental group, right? So it's a torus minus puncture mod Z2, right? So you take a fundamental region, and you consider like a quarter of it. And then, so here X is the A cycle. So the star is a puncture, right? And then X and Y will be A and B cycles of the torus, right? The holonomic around A and B cycles, and T is the half turn around the this is the puncture. Yes, this is puncture, right? And then so say there's a point, and there's this image under Z2, and then T is the half turn, right? And so we have these relations here, which are color coded, right? And the green relation is the fundamental group relation for the torus with the puncture, right?
But what is the Z2 after the torus?
So we have just Z so we have a plane, we have fundamental domain of the torus, and like the coordinates code X goes to minus X.
X goes to minus X.
Yeah, so for example, so yeah, so this is the origin, right? No, not different X. Let's say this is the like a complex plane, say complex plane U. Let's go. U is the complex plane variable, and then symmetry goes U goes to minus U. Right. Oh, but therefore, I mean, they're the same, right? So it's a okay. And then on top of this, you have a lattice. I have a torus lattice, right? So it's the same point here, here, and here. They're all for this. Okay, and then yeah. So so this is what is called affine braid group with this relation. So then the central extension of that, you add this parameter q, and that deforms you to this relation in DAHA. Come on.
What do you mean that? How we form the group?
It's the fundamental group of this surface, which I just described, right? So you describe this topological space as the quotient. You have, torus description as a lattice and complex plane, and then there's additional Z2 action.
So suppose I go around a fixed point twice, is that compatible?
Yes, yes. Good point. Fine. Good. So full DAHA again is this. These are generators, and these are the relations in the same quantization. Okay. Now symmetries. So this construction admits a bunch of symmetries, which will be important for later. So there's a discrete what's called a theta symmetry, which is Z2 cross Z2. It acts on it inverts signs of x and y respectively, and does nothing with q and t. And then the mapping class group of the torus also acts on all the generators, right? So tau plus, tau minus, and sigma. Right, so just the standard one. So you should think of tau plus as something like 1, 1, 0, 1, right? And tau minus is the other one. And there is also this nonlinear involution, iota or iota tilde, which negates the t, and it also inverts the little t, which is also the symmetry. Okay. Then, so that's already quite complicated. In fact, the way DAHA appears in this deformation quantization, it's in its spherical form, right? So we take the idempotent element E, which is this, and then we sandwich every element from DAHA between those E's, right? So and by doing so, we symmetrize every generator, right? Every element now becomes symmetric in big X, big Y. So all of them become symmetric. And we can rewrite those relations in the following way. So if little x is x plus x inverse, little y is little y plus y inverse, and little z is this combination, then the relations are as follows. So the cyclic q commutators between x, y, and z, right? So x, y, and z commute, q commute. So this is the q commutator to z, and cyclically as well. Y z equals q, x, and z x equals y with this coefficient, right? And in addition to that, this combination here, which is x, well, this one on the left, so it's a cubic in x, y, and z, and there's some factors of q spread around. It's a constant, right? So it's like if you like, it's an analog of the Casimir element, right? So it acts for the constant.
Gives a motivation for why people consider spherical DAHA.
Well, so in geometric quantization, it appears in spherical form, right? So literally, like this little x will be monoderm of the A cycle, y will be monoderm of the B cycle, and z is related to the monoderm around the puncture. And also in physics, when we study gauge invariant operators, they're always invariant under this while group Z2, right? So I'll tell in the end how to get full DAHA. It's also possible, but kind of most naturally in this kind of quantization approach, you get spherical DAHA.
So this big x inverse, let's think of this isomorphic matrix.
Yes,
like,
yeah, that's right. Yeah, so right, yeah, that's how you should think of, say, so you have a torus, then the sort of monoderm around the A cycle should look like big X inverse, like this. Other questions?
And the space itself is a Coulomb branch of
3D. So, okay, maybe I can show this last slide. I won't have time anyway to get there.
Sorry.
So you have to answer physics questions. Yeah, so how to get DAHA from line operators into star theory? You take, okay, so it's n equals to star theory on, something's missing here. Okay, no, I'm right. So yeah, so basically we have we have a two-star theory on in omega background, right? So it's on R2 cross R cross S1, right? And you look at line operators into star theory that wrap S1, and there are operators of three types. There's a Wilson line, there's a monopole line, and then there's a dionic line. So these are exactly X, Y, and Z. So the reason why they don't commute is because you put them like a background, right? And they become point-like on this line, right? And as you commute them around, there's a price to pay, right? So kind of more formally, you have, well, maybe I can show it right now. You have some category of line operators in this theory, right? Which is some dB coho of Z, where Z is this affine Steinberg variety. So those who work on Coulomb branches, those terms should be familiar, right? And you take K naught, like the K theory of that category will be spherical DAHA. Yeah. What? Is another question? No, I'll make it hard. Okay. Thank you. Yeah, but most relevant contact will be in larger font. Is this good enough, or is it still too small? Oh, that's fine. Okay. Okay. Right. So let's talk about those flat connections again. So we have a fundamental group of the punctured torus. Right. This is a SO2C representation. So X, Y, and Z. So X is the image under this map of meridian, or like A cycle. L, Y is the image of the longitude, or B cycle, and then like trace of one times the inverse of the other is the third guy, right? So and then I think I forgot to say, right? So if you take something was missing from that slide, yeah, and then so if you take the classical limit Q to 1, right, then you get so all Q's become 1, right, and this relation goes into this cubic, right? So if the coordinate ring of the modular space of flat connections, you can describe it like this, right? So the here, so it's called Markov cubic for in this three-dimensional complex space. Yeah, so this is what you get. The relations in defining the relations will give you this equation, right? So it's a one complex equation and three complex dimensions. So it's a two-dimensional space, and it's one of those. It turns out that this is an elliptic vibration of Cadaver type I0, which means that it's, well, I'll show you in the next slide how the vibration looks like. But so what Ablonkov shown is that the spherical DAHA is this flat one-parameter deformation or deformation quantization of the coordinate ring on the moduli space of SL2C flat connections with respect to the following Poisson structure omega j, which is this Atiyah-Bott structure. So you have dx wedge dy divided by df over dz, where f is the left-hand side of this equation, right? So it's dx wedge dy over 2z minus xy. So what we'll do next is that we'll discuss representations of this DAHA, spherical DAHA, and then we will describe Lagrangian submanifolds in X. I'm going to call this moduli space X for short, whose quantization, well, in the sense that it comes along with the Branes and quantization program, yields the representations, and those Lagrangians will be objects in the Hecke category, right? So we'll find a connection between the representation category and some category of A-branes. This Z?
Yeah, like X, like a meridian.
Well, I mean, okay, so you can, right, if you like, you can take this monitor on the puncture, but it's related to the other two, right? So there's a, if you like, there are three generators in one relation, and it's up to you how you describe it, right?
Obvious the way. So originally, DAHA was discovered in the early 90s in the work of Cherednik and simultaneously Koroteev.
I think so, yeah.
And Koroteev was thinking about Transaimus theory on torus with the puncture, and of course in Transaimus theory,
you mean like was it somebody before Ablonkov? Like Ablonkov actually showed that this in this particular complex structure, you get the algebra. Yeah. No, probably people are thinking that.
I think it's not surprising given Kirillov's old work.
Yeah, I think it makes all this. He referenced that. Yeah. Good. So yeah, and then the right. So what's the main statement? that, well, in this branes and quantization program, we will be studying so-called canonical quasi-tropic branes, whose and the space of open strings between this brane and itself, like this algebra of endomorphism of the BCC brane, will provide the quantization of this coordinate ring. So this will give us the algebra. So in other words, the BCC strings will give us the algebra, DAHA, and it will allow us to make a derived equivalence between the category of A-branes on X with certain symplectic form omega curly X into the category of representations of this algebra. So I don't know how to prove this in general, but I know how to prove a restriction, how to prove a certain specification. So for when X is in flat, so in fact, this should be true in general in some sense, right? And I believe that the Kensevich and Sobelemann's program in part will shed some light on the statement. But what I will show you today, at least give you the idea how this is computed, is that this functor here restricts to the equivalence between the subcategory of compact Lagrangian A-branes and category of finite-dimensional DAHA modules. So that I hope I'll be able to convince you that this is true.
Sorry, you point us the meaning of the two factors.
Yeah, so TR, so it appears in this either Hecke relation or geometrically it comes from the puncture, right? So it comes from the hole around the puncture, right? Q here, it arises as a quantization parameter, right? And on the Foucault side, it will come from the B field in a sense. It will be so when you do the quantization, you can allow your Planck's constant to be complex, right? And then Q will be related to the phase of the, well, not only, but also in part will be related to the phase of the Planck's constant. Like phase and the value of the Planck, yeah, so Q will be, sorry, I'm saying something stupid. Q is just e to the 2 pi I h bar. Right. So if h bar is a quantization parameter, Q is the exponential of h bar.
Your definition of that has relations.
Yeah. In the torus here. So if there is no Q, because in fact, yeah, so right, so you see if there's no Q, this is called affine braid group, right? If this is one. And then if you deform it on the right-hand side, you'll get DAHA. Yeah, that's, yeah. Yeah.
Yeah. There's some better set of parameters for this whole, or we have something like this.
So as far as sort of this, so for this, I don't know.
Like in the story, you have to have some kind of condition. So this is this category of representation. Yeah, there's some sort of conditional parameters.
So yes, also so I will specify Q and T for which we'll have finite dimensional representations, and for those we have the full equivalence. So there's
always in any algebra has finite representation.
What kind of parameters are you talking about? What? Q? What kind of parameters? Q and T or?
I don't know. There's some parameters that just interior. Maybe Q is like the distribution strength.
Yeah, Q is e to the h bar. Yes. So, well, for generic Q and T, you should expect an infinite dimensional representation. For certain specific values of Q and T, I'll show you the table. We have a classification of all finite dimensional. Am I saying? Yeah. So I can identify all finite dimensional, all irreducible finite dimensional representations for certain values of Q and T. And then I can also identify reducible but indecomposable representations for certain values. So basically, yeah. So generically, it's not even, they're not finite. Yeah. So if this fails for some other values of Q and T, this I don't know. But I'm only working with this specification here. Does that make sense? So
you're proving this code for some specific values?
Yeah, there will be a table. So we'll get to the second. Yeah, so there will be a table, some values of Q and T, for which I have finite dimensional representations here and compact Lagrangians there. And there I have a match. Like the dimension of the representation is equal to dimension of the space of open strings between two branes. Basically, I compute a Riemann-Roch formula. It gives me the dimension of the representation in units of the Planck's constant. And so what's the Vizor-Karnikov story? Where was
so T must be some kind of, T has some kind of meaning on the other side. T is something.
What Q? I mean, they both will be related to the B field. I mean, on the right. Yeah, that's right. Yeah. So.
But what's the meaning of Q?
Well, I mean, the way B field enters the story is also Q depends on that as well, right? So, yeah, let me show the formula. So through the phase. Let's go to BCC brane. Here, no, before that. There. So this is the so if omega j that's a symplectic form, right? It divides by h bar, right? And then so h bar comes from q, right? It's the log q, and then it's basically there's a real part and imaginary part, and it kind of all mixes together.
Suppose I have a Lagrange, right? Then this parameter is kind of multiplies by form.
Yes.
So one is for which values of the parameter is that Lagrange?
So I'll give you an example. So for see, it's very technical. So here's an example. So you have what is called modular space of G bundles, right? Which is called V when T squared is equal to negative Q to the minus K. So that gives you the compact Lagrange.
No, that is like, no, that's a definition I understand. What does it mean if you some kind of conditional Q
Yeah. So that, right, so this say, this is so-called the generic fiber. So there's no it's an elliptic vibration, so you have a compact fiber, right? And you can quantize it. So it turns out that Q needs to be root of unity for this fiber to be, for the quantization to take place.
Wait, but the ordinary Lagrangian inverse don't know about it at all. It's only the BCC brane that knows about it.
No, because hold on, where is it here? Let me do it.
Your omega j is
right,
so again, you're doing some A model. And
yes.
What is the symplectic form of the A model? Is that omega j? Is that
it's yes, it's this almost omega j that I wrote before divided by h bar, right? And you take imaginary part of that.
And that's the symplectic form.
That's the symplectic form. So I want to rotate my twistor parameter as I change the parameters of the vibration. I mean, so it just as you change the phase, it just stops being homomorphic in one complex structure. You have to rotate it, right? So it's the.
Oh, I see. Are you making H bar complex?
Yes. H is by itself is complex. But that.
So it's not the field. It's also it's like so like the volume that is integer.
Yeah. Literally. So here's an example. So see, because it's two-dimensional, so this is the Riemann-Roch formula, right? And then it boils down to just computing the flux. Because like the thought class is just, Chern root of canonical times the A roof, and then it cancels, right? So you get just F plus B over 2 pi. So basically that must be integer. Yeah. Okay, why don't we continue? And then, so I believe some of the questions will get resolved. Yeah, I know. Like, imagine doing this on the blackboard, right? So, okay, I think, let's talk about. Anyhow, so this is what we're striving for. Like the kind of global goal is to better understand this statement and similar statements around those lines. And I believe Mina, with her students and postdocs, is working on that.
You say we have some last sentence. You have equivalence for specific categories in specific places. The test is restricted. There's some generic equivalence.
Yeah, so we believe that this is a generic equivalence.
And I was asking, that generic equivalence, where does it fit?
On,
Is there some place where it actually fits?
on this I don't know. I mean, it's so we believe that this something like this should hold because, well, it's just sort of the general expectation. So you have a space, right? You quantize it, you get algebra, some algebra, which is the formation of the algebra functions, and then there is a Fourier category, right, or some kind of extension of the Fourier category, and they should not be. There should be some connection between them, right? So to say exactly which one is part of the question, but we claim that if you look on that compact Lagrangian branes, then we have a precise map. And not just the object, but also extensions. We can compute homes like home one. Yeah. So it's not just a set theoretic, but just a category equivalence. Yeah. But as mentioned, Bezrukavnikov, so in which sense their statement fails for the
we have an algebra, you know, there's some kind of notion of that algebra being That's basically field.
Ah, so there's some jump kind of dimension. So okay, again, maybe other. So I would hope that for this simple example of rank 1, there's no such thing, but maybe possible. Even like for small rank, they have issues.
So then of course, what's the quantization?
Mm-hmm.
You get SO2 which means central charge. SO2 is the central charge where you take the, you know, the highest weight minus 1.
Yes.
You don't have any kind of.
Okay, yes, yeah. I see. Yeah, I haven't thought in those, yeah, but I see. So yeah, right. Okay, good point. Yeah. Okay. Okay, let's talk about polynomial representation. So, well, so how does it work? So let's. I think we have time. So x with the multiplication, yx with this Magdalene operator. So omega is the shift, right? So just x multiplies x by q, and z is some well blended combination, right? So
connecting with what Andrei was asking, we could have done all this for simpler space. We just did the
T-star
right? The case that was done in
Gulkov Witten.
Yes. So are you doing what you're doing here as a generalization of what they
Yes,
want?
yeah, that's right. Only that. So here, like there, they had certain continuous symmetry, some U1 symmetry, which is kind of, you know, of the thing. Here, there's the role of that continuous symmetry is somewhat replaced by this discrete symmetry. So like those branes will be invariant. They'll occupy some invariant loci under those reflections, and that would map to certain conditions on existence of those branes. Like conceptually, it's along those lines, but details are different. Yeah, so if you're familiar with Gulkov and Witten's paper, we're doing branes and quantization for DAHA, but of course, we want to go beyond. We want to understand this in as much as possible. Good. So I don't have to tell about all the details, but this I have to tell. So this is how generators act, right? So there's a shift operator, and then there are two shift operators and multiplication, right? And then oh no, of course not, right? Yeah. So in that sense, it's an upgrade. Yes. Yeah. So right. So the and then you can ask what's the highest weight vector and highest weight. So let's call it z. Now, if you don't think about polynomials per se, but just ask for sort of general boundary conditions, what is the solution of this difference equation? Right. That it turns out that you can have an interesting series of hypergeometric type, and it appears in this enumerative geometry calculations, which were done by Andrei, and then also Anton and I, we made a lot of work on those. So kind of, in fact, this is how I got into this project, because by observing that there's a hypergeometric series, and then if you impose certain conditions, like you put this parameter a on a lattice, right, and it truncates. Like all those corrections, they vanish simply because of the structure of hypergeometric functions. Once it's 0, all other orders are also zero. We have this Pockhammer Q factorials, right? And it's an interesting phenomenon. So you have the series representation, and then there is a yes. If you take A is equal to Q to the JT, then we get this spin J half representation. You know, it's like in quantum mechanics. You have a hydrogen atom Schrodinger equation and the wave, what's it, angular wave function, right? If L is not integer, it's a series. But once the angular momentum is an integer, it becomes a polynomial, and that's how you get your periodic table, right? By changing L. So here's the same idea.
So question. So about the definitions, you have this H double dot, H double dot. So far, there's nothing about Z2, right?
Oh, yeah, so it's always the same thing. So like it's just the notation. So Z2 is there for the while group. So it's the just if you want ignore Z2. So it's that spherical DAHA that I described. There's no other definition. It's part of the construction, right? So for SLN, you would expect Zn or something like that. There's it's the while group that this manifests.
You give me a torus, I can have like it's another top, have a Z2 action, have a Z3 action, have other.
So if you want a Z3 action, you would want to study SL3 connections, I think. Yeah, so that's what the you get. So in order to get DAHA this way, you'd have to take Z3 mod Z3, right? Action quotient by the action of the cubic root.
And the Z2 action is it's acting on the torus.
Yes.
And
it's like
fix the puncture.
Yeah, you can put puncture in the fixed point of this involution, right? So as in that picture.
Put the puncture.
Yeah.
On the fixed point.
On the fixed point. It's point. It's all the same, right? So. Okay, let's move on. So now, yeah. So if you truncate those, you get polynomials, right? So these are Macdonald polynomials. And here are the first few, P1, P2, P3, and if you wish, P0 is equal to 1, right? So they're symmetric in X, and the coefficients are rational functions of Q and T. Right? Now, how do we gain this? So what can we do? So we can rewrite DAHA generators yet another way. So we keep Y, which acts by constant on those P's, and we can create raising operator and lowering operator. So here, the way I wrote them, they depend on index of the polynomial. But if you really want them not to be dependent on index, you can do that. But anyhow, so R sub j is this combination of X and Z, and L sub j is a different combination of X and Z. And then if you hit polynomial P sub j with R, you get well this factor here and times Pj plus 1. And if you activate the lowering operator, you get the rational function, right? Times Pj minus 1. And this rational function can vanish, right? So if it does so, then what happens is that so you go from Pj goes to Pj minus 1, you activate the lowering operator, and you get 0, right? So this way you cut your module into a submodule S, and then there's a factor module here, which has a dimension of j. It's a representation of dimension j. And now if you analyze this. The function, you see that it must vanish in exactly 3 cases, right? Q is an even root of unity, this relation and that relation. Notice that the denominator does not give you, so like it's the raising operator cannot vanish because the same function appears in the denominator.
So just making sure these PIs are
you want the formula?
Yeah, go back. Yeah.
Sorry. Yeah, I'm coming. Yeah. So 2 phi 1 is the Q hypergeometric function. It's a generalization of F to 1. So claim is that like functional solution of this equation is this 2 phi 1.
So these polynomials, they are.
Yeah. So they provide you the like basis in the representation.
There's no Y. That's the difference. Like that's
no Y acts with the so Y, right? So
there's no big Y.
big Y. No, yeah. So if you like, this is big Y. This is big Y inverse. That's how it acts. So big Y acts with this term. Big Y inverse acts with this term. If you want to do the representation of full DAHA, you can do it. Yeah, it's written in Cherednik's book, and that's what it comes down to. So here, just a symmetrization. Okay. Anyhow, so these are the three cases, and then the table that I showed you before it sort of illustrates them all. Okay. Now let's talk about the geometry. So you want to write the modular space of flat connection as modular space of Higgs bundles by employing so-called non-abelian Hodge correspondence, right? So you want to rewrite the so the solutions. So the way it works, you take the Hitchin equations. You take the Higgs bundle, right? You have Higgs bundle, which is an E comma phi. So phi is the Higgs field, right? It's a section of this bundle, canonical. So CP is the torus of the puncture, right? So you have a canonical times everything values in adjoint representation time tensor the bundle O of P, which provides the ramification data for the connection in the Higgs field. So basically, you have these three parameters: alpha, beta, and gamma, which I will be talking a lot in the following, and they tell you the kind of the deficit angle and the singularity data for the.
You're trying to describe differently the space of time.
Yeah, that's right. Yeah. Right. So and then the way this correspondence works is that the space of solutions of Young-Mills-Higgs equations is an one-to-one correspondence with those of the flatness condition if you have this sort of non-holomorphic change of variables, right? So it has a complex flat connection, and you say it's this real connection from Higgs theory to plus I times the real part of the Higgs field. Okay, and then it's a hyperkähler space, right? It has three Kähler forms, which are computed with different combinations of derivations of connection on the Higgs field. You can write down the triplet of holomorphic symplectic forms from those: big omega I, big omega J, big omega K, with a cyclic structure depending on the other guys, and then depending on which complex structure you pick, like different parameters, they describe your Kähler moduli and complex moduli. And then so we will want to change those as we go, because as I said, Planck's constants will have a phase. They are the singularities of, so P is the puncture on the torus, right? So you have a Higgs bundle on the torus, and then alpha, beta, gamma are these numbers. So if theta is some angle in the local trivialization around the puncture, so it's like a deficit angle, right? So you have a singularity, right? And these are these numbers, they will parameterize.
They're locally near.
Yeah, locally near the puncture. This is how it looks like. Because we want to describe singular fiber, right? Remember, it's an elliptic vibration. There's a singular fiber, right? And these guys, these three letters, will describe the they will for different values of alpha, beta, gamma, will have different singularities. You'll see in a second. Okay, so good. Right. So just mostly repetition. So so then under this correspondence, the holonomy around the puncture that will be related to this matrix over here. Right. So remember, alpha and beta matrix valued the matrices, right? So so T is related to alpha and gamma, right? So when T is equal to 1, so we work with n equals 4 theory in physics language, then the space is just C star cross C star mod Z2.
What if you could change
Yeah, that's right. Yeah, that's right. So but it's the same. It's the same Z2 as in this orbifold construction, which always kind of.
So mine is not F.
Sorry.
Mine is not F.
It's the if you have a so no, you have a so you have an orbifold fundamental group of you have the torus. What is it? Torus T2 minus point mod Z2. It's not. Hold on, I need to. No, so never mind. Yes, this exchange the factors. It's just the that's a different. Yeah, and then the real slice is just S1 cross S1 mod Z2, which is the pure case. Right. You're right. In the sense, like Z, I mean like the big Z. of the.
Like C stars, because C stars, like preserving each factor changes C equals to 1 over Z.
Oh, yeah, you're right.
Yes, that's the.
I think that's right. Yeah. Yeah. I think that. Yeah, I always forget. Okay.
It looks like it's just a 1 4. Shouldn't it be Hassel's probably?
Yeah, it's a matrix.
That's a matrix, but
Yeah.
then you wrote it as
Matrix.
it's a matrix on the left, but on the right, those are just numbers.
No, you can exponentiate a matrix, right?
Oh, okay.
Yeah. I mean, if it's diagonal, it's just exponential eigenvalues, but yeah. So you should think of T as a C star valued thing. Yeah. Okay, good. So now, so let's say all of those parameters are 0, right? So how does this vibration looks like? So then, so we have the pre-image of the generic point under the projection is the generic fiber. It's just elliptic curve, right? And then there is a pre-image of the origin. It was called the Neal cone. So it turns out that sort of it looks like this. It looks like a 5 P1s, sort of 5 rational components connected together like that, right? So if you sort of fully resolve all the singularities, this is how it will look like. So it has this form of the, it has the shape of the affine D4 Dynkin diagram, right? And then, well, sort of in what follows, I'll describe the kind of volumes of each of those P1s, and then in some combination that would correspond to the finite dimensional representations of DAHA. So if beta, if you turn on beta, right? So then if T is equal to 1, then these 4 corners, these 4 P1s, they shrink to points, and you get this pillowcase, right? And as you change the T, as you increase the T, it essentially dials the volume of those P1s. They're called exceptional divisors, right? And then in this case, we have a holomorphic Lagrangian with respect to omega I, or it's called brane of type BAA. Now, yeah, and then okay, let's skip that. Now
So how does things depend on this choice of factors? So those pictures are only for the special case, everything is 0.
So this is So no pillowcase. If everything is 0, you had this well with the C star cross C star mod Z2. If you change alpha, right, then you blow up those P1s on the side. This D1, D2, D3, D4. So keep beta and gamma 0, but just crank up alpha.
And
right?
In the complex structure you're working with, eventually with the A-branes, changing alpha is changing the complex structure.
Let me look it up. Scalar. So in complex structure I, it's the scalar.
But you're working complex structure J. Your
Yes,
A-branes are A-branes.
yeah. Complex structure. Yeah, that's right. So it's also changes.
So you're varying complex structure.
No, you keep the complex structure, you vary the modulus, right?
Yeah, you're changing complex structure. Sorry, you're saying your complex structure J means that its symplectic form is omega J.
Yes, that's what I said.
And you're keeping the symplectic form fixed, but you're changing the complex structure.
That's right. Okay, so good. And then, but turns out that if you change, if you pick up generic values of beta and gamma, then the singular structure of the.
Wait. So as soon as you turn on some parameters, the space becomes smooth.
Yes, that's right. Yeah, and as you see from this picture, that even the type of singularity can change. So from I0 star to I2. So when beta and gamma are turned on, then so this embedding of the cycles D, the exceptional divisors in the middle, V, the band G into moduli space of Higgs bundles is no longer holomorphic with respect to I, right? And then so if you want to preserve holomorphy, right? So it's actually it splits into kind of these 3 singular fibers of type I2, right? So you have so like have 3 singularities, B1, B2, B3 on the base, and then each of them has 2 P1s with 2 double points, right?
But you probably don't want to work with that.
No, I do. I will identify representations corresponding to this. So that's one of the cases on the table. So it turns out that we were missing this initially. So initially we thought about this D4 diagram, but turns out that this also gives you something. So you don't want to turn on those beta and gamma to see some of the finite dimensional representations.
So you work for generic alpha, beta, gamma,
Yes.
but then your A model is not,
Basically, so
does not have any effect.
right. So in those cases, so because I can always turn it into some exact symplectic form by tuning the B field, right, and the Planck's constant. So in the end of the day, I'll have a list of cases where I have compact Lagrangian branes in certain symplectic like BA or ABA or whatever, right, for some certain values of Q and T, which translate into certain choice of beta and gamma and alpha. Yeah, so that's the idea. Okay, so then basically you can compute those integrals. Yeah, basically you can see that integrals over V over omega I jk gives you these guys. So some formula that relates geometry with the data of the Higgs bundle. And basically, so you can compute, right? You can integrate any form around everything, and you compute some function of alpha, beta, and gamma and stuff like that. And then there's also the symmetries, actual discrete symmetries around it. Okay, and so then to get the algebra, you need to introduce this quasi-tropic branes. What is it? Is the Lagrangian fibration, right, over, in this case, X, which is the whole space with a first term class, which is the curvature of this bundle. And we studied 2D sigma model, A model on X, right? And then the family of those BCC branes will be parameterized by H bar, right, in the symplectic, on the symplectic manifold. I think it is a form, yeah, here. So the, how it was raised. There was a formula here which got erased. So it's this omega, I'm going to write it here. So symplectic form is imaginary part of omega j divided by I h bar. So this is omega, little omega curly x. Okay, and then so quantization parameter is exponential to the pi I h bar. So we also introduce the B field, and then these values of B field and F are determined by this equation. So if H bar is complex, then the real part of omega gives you the F plus B, and imaginary part of omega gives you the symplectic form. So if H bar is real, we have BA branes, and if it's pure imaginary, we have AAB branes. And this is the hyperkähler condition. So so the idea is that this home of BCC parameterized by the Planck's constant, it provides the deformation of space of homomorphic functions on S, and it gives us the spherical double affine Hecke algebra. And the way it acts on the representations is the following. So we can merge, we can combine open strings. So this is how algebra acts, we can combine generators in algebra. And if B prime is the Lagrangian brane, which corresponds to the representation, then by combining BCC string and BCC B prime string, we'll get action of algebra on this representation. So I don't want to keep you too long with technical details. Maybe I'll describe you one calculation and then I'll just show you the table, right? And we can talk about that. So now if you have a Lagrangian brane, so it's not just a subspace, right? It has more structure to it, right? So what you want in Fukaya category, you want to have the brane itself, like its support. So it's a unitary bundle. You need to make a choice of flat spin C structure and what is called the grade lift, right? All three components are important. So the reason why you might need a spin C structure is because you might not have a kind of Lagrangian brane on its own, but if you tensor it with the square root of canonical, it will become an honest bundle, meaning that if you take gluing functions around, so you have three charts overlapping, right? And you want to take the phi ij, phi jk, phi ki, it may not be equal to identity, but it can be equal to -1, right? And you have to account for this choice, right? And then using the Riemann-Herzebruch Roch formula, you can compute the dimension of this space of sections, right? Of this bundle. So it's in physics language, is the dimension of the space of open strings between this Lagrangian brane and the BCC brane. So it's given by this standard formula, which specializes for the case in question, because it's a two-dimensional complex variety, to just integral over the Chorn class of the BCC brane over the Lagrangian.
So you're working some complex structure where you're.
Yes,
brane is a B-brane.
yes, that's right. That's why it says B model for the. Okay.
So your F prime now is the
It's the curvature for the for L prime. For L prime. It's the B field. It's a two form, right? So in fact, see, first Chorn class of L F is quantized at the unit of 2 pi, but this is not. This is continuous, right? So that will allow you to, put in some continuous parameters like Planck's constant and stuff like that. Mm-hmm.
Like I said, always afraid of this top class. Why did it show that? Or just
Yeah, yeah, certain conversation. I mean, for surfaces, there's a simple version of the formula, right? You don't have to write it in the generality, right? But yeah, so it, like I said, it simplifies this too. Okay, so how you're still okay, guys, right? Not toasted yet. I can go like for.
I thought
Okay. Yeah. Yeah, but since okay. Anyhow, so now I don't want to talk about this. Remember, I mentioned to you that you have Macdonald polynomial. You actually not always have a polynomial, but you have a series, and then it can truncate into polynomial if you specify some conditions. So now let me go back to that because it gives you some interesting geometric perspective. Now let me twist my operators. I'm going to put some y1 here, and that will explain partly how the spin C structure works, right? So we have, so how should okay, so geometrically, so that's what Pen was asking. So think of, maybe we can get this one right. So we have C star cross C star mod Z2, right? And then there's some brane, some Lagrangian brane on C star mod C star cross C star mod Z2. So you can have branes of two types. You can have like this torus with two red circles, or you can have a point on one, right? And it can wrap the other factor. So the position of this y1, so if you talk about branes of the second kind, when they wrap one C star and they just a point on another one. So this y1 choice of the y1 on the other C star will be related to the spin structure, right? So what is it? So we have so we have how do we define spin structure in general, right? So we have if you have non-trivial cycles like on a torus, you can have holonomials around each cycle, so you can compute those holonomials. They'll give you some values, right? And then so the absolute values of those holonomials that give you the spin structure, and spin C structure on top of this is a certain choice of sign, which comes from the fermions, fermionic degrees of freedom at the left and right boundary conditions when you study open string. So there's a +1 for Ramon sector, there's -1 for the Nevers-Schwartz sector. So in general, your choice of brane would be dependent on the support and also on the choice of this lambda, right? So this data of holonomials, which I denote with x sub m and y sub m. Okay, and in the representation theoretically, it manifests itself in the following way. So if I put these factors y1 here, so I go back to this infinite dimensional representation, right? I can consider this module, this multiplicative structure, when I have, well, this ring is generated by all factors of the sort. So I have q to the L x minus q to the minus L x inverse, right? And then for all possible L's, right? Then I can consider, yes, then this is how this, then I get back to the series solution, right? To this Q hypergeometric function, right? And this is the eigenvalue. So my brane is supported. So brane corresponding to this polynomial representation P is supported over here, basically under this value, right? And if I truncate this, I get back to my polynomial. So turns out that I can by picking different spin structures by
Sorry,
picking.
can you go a little slower? But I'm not following.
Okay, so I want to describe various polynomial representations that arise from taking Lagrangian, which is the generic fiber, right, the torus. Right, so
Can
in
you
the,
draw a picture of your space, or it's not, so we can have it down?
yeah, so the, I mean, it's just torus over the affine base, right? So it's the, so say, you know, over the origin, you have this D4 diagram, right? And then the generic point, you have a Riemann surface. So I'm talking, this is called F, right? And this is what the knee cone, like n inversely. So here I talk about the torus. Okay, so representation theoretically I can do that. I can introduce this factor, right? And then talk about infinite dimensional representations. And then I can say, well, for which values of y1 will I have a truncation? And I told you how, right? I told you that if you take this vector and specify y1 equals to q to the negative j, you
So
get.
what's the, sorry, what's the picture of brane? I mean, what's the support of brane corresponding to infinite dimensional? We'll just go a little bit more slowly.
Yeah, so, right. So support is still the same. It's a Lagrangian brane with this torus, right? It's a support is the same. What I'm changing is the spin structure.
So your base is
Yeah.
a plane.
Yes.
Your fibers are torus. Which looks like
No, no. So Lagrangian wraps this, right?
Where's the brane?
Yeah. So this is my
It's
B, what I call
normal structure.
BF, and then there's a choice of spin structure. Right. And then. So yeah, you're asking about B. It's a A-brane, right? So here, theta, it's the phase of Planck's constant is 0.
So, and this brane can be anywhere in space.
Except the origin. Yeah. So when I approach the origin, it sort of splits into this.
And that brane is said to respond to infinite dimensional representation of DAHA.
For generic values of y1. Well, here's why. Because you have, I mean, unless this value is certain, lies on certain lattice, then you don't have a finite dimensional thing. So basically, I'm telling you that this y is related to, well, location of this brane on the space, right? So if you think about C star cross C star picture for the moment, this is how this brane looks like, right? It wraps the one factor, it's a point on the other, and turns out that the quantization condition on these terms boils down to. No, sorry, hold on. Yeah, so there are two. I'm sorry, guys. There are two. Yeah, good point. Thank you. Right. So the I apologize. The generic indeed. So generic fiber is the torus. Is these two circles. Yeah. Right. But still there are this U1 squared holonomics, right? And you need to specify those values. Yeah, thank you. Yeah, so this is a different module. It's a different representation. So that is always infinite dimension. Okay, and then so what to do here is that right. So first you compute this space of Holmes.
Can we just slow down? I don't understand what brane you're talking about.
I'm talking about this red. So you have this. It wraps the circle here. It wraps the circle there. I see. Basically, it's this one. It's the one I initially described, right? So it's the. Which is called BF lambda. Right, and lambda is the choice of this U1 holonomics. Yeah, so xm, xy, choice of those holonomics, right? And now what I'm, come on, how is it? Yeah, and now so it turns out that the action of DAHA on this representation, it commutes with this x to the m minus little x to the m. And this ideal xm minus little x to the m is invariant under the polynomial representation, so we can quotient by it, right? So we take this py1, and then we quotient by this this factor, and we get m-dimensional representation if we say that ym. Guys, I think I'm messing up the. it's a different brane. Okay, no, okay. I think Andre was right. I'm sorry. Yeah. So if it, yeah, I apologize. If the brane is compact, it's always finite dimensional, and that corresponds to Q being even root of unity. If it's non-compact like this one, then I can play this game. Yeah. I just to get confused. Do you understand what I
The
mean?
non-compact brane will just be supporting the base.
Yeah, it will be like base and then like yeah. So it will wrap the base and the point here. Yeah. So the right, but yeah, so you can make sense of that as well, right? By sort of but sorry, so where's my back? Show the picture. So if we have this compact brane which wraps the generic fiber, it corresponds to Q being a root of unity, and M is one of the Planck's constant, but Planck's constant is real. But we can also make sense of those infinite dimensional representations when the when we sort of specify certain condition on this y, namely, if the y1 to the m is equal to ym, and ym is the Coulomb around the circle, then the and then sorry, ym is that position, then we have another finite dimensional representation. And if we specify this y1 to 1, as in kind of polynomial representation, then we'll get this guy. We'll get p mod x to the m plus x to the minus m minus this thing. Yeah. So
When you say you get, how do you store this?
just the computation. I mean, so which part? So the like this part that it's a quotient.
How do you map module to algebra to brane?
You compute. So you compute. So you compute this, right? You compute this integral, and then you impose the WQB quantization condition, right? Because it's a compact space, H Planck's constant must be 1 over the integer, and then you just compare with the dimensional representation. That's the first test, but there is more to it, right? Because the you can also how this how the branes intersect, and how the representations talk to each other. How they I'll describe it next. But first, you can just match the dimensions. Yeah.
I don't know if it's a good place to ask this question. So a couple of weeks ago, we had a talk,
Vivek?
gives you kind of opportunity to do it, rigorously. Is there a structure of the skeleton here, something like that?
My understanding is that sort of this is the skeleton, right? Okay.
Is it like the next theory is the fly?
Yeah, it couldn't be.
What is that? Because it's like this process, right? There are two algebras in the story, in principle, right? There's the recursive algebra of quantization of Coulomb, right? And then there's the other algebra, which is the algebra of the immortal tilting factor of Coulomb. I think all Coulomb branches should be describable. I mean, you should be able to. For all Coulomb branches, I think we could run our story and get a mirror of the tilting bundle and just solve the theory that way. That doesn't speak. I mean, so there you can just there we have the technology, I think, to describe the one. There's something modular directly, like, but in the following sense, you draw me a brane, I can tell you how it converts into generators. He's doing it different.
Okay, great.
Yeah.
I understand there's this more powerful story too, so I don't know. I didn't know that's a fair question to ask now.
Okay. Yeah, let's discuss it. Let's discuss it later.
But I guess my question is I don't know if it's going to be like more naturally projected to your story or to the next story or to both of them. But the first step, we made some kind of statements about
A-branes and
some kind of branes.
Mhm.
About the brain. First, project to some kind of other mathematics or something. Modules over some algebra or
Mhm.
sheet or something like that. topology through that step that already exists.
Yeah, the question can be asked like, what's the issue on that set of simple fiber?
I mean, like some derived, it's a DP call. General cases of what?
No, but here you would just,
Kitchen vibration.
I think maybe
Ask.
the question is whether in your, the way you guys describe crack fiber when projecting everything to the skeleton, you get naturally some kind of quantization problem with that naturally associates the D module to your brain, right? Which is.
I understand it's not exactly a difference, but I was just wondering if, since you started with the beginning to, I don't know, you gave some description. I thought you said that this is somehow like a physics level right now.
Yeah, at the moment, it's like the top correspondence at physics level, and then kind of I'm giving you the
My
match.
question is, there's some kind of like math foundation, but okay, I'm not the expert on this. I refer to.
So my understanding of the current state was from that Kontsevich Sobelman that slide when I had like 4. So I think, but they don't have a paper yet, right? No, they're giving talks around like for like 7 or 10 years, but I think they claim to know how to construct what like a BCC brane is and how this endomorphism algebra can be constructed, but I don't know any details. Like,
this was at that time.
okay, good. So
there must be some kind of more direct way to match something to something as opposed to
well, but not only not only compute dimensions, but also check like it's you can compute some forms, right, on one side and on the other side. I'll have a couple of examples, and yeah. So I agree. So I don't know. So I mean that's why we did what we did. But do you guys think that there's a certain canonical prescription which allows you to, given a brane, obtain a D module or some kind of differential operator, or they're shaking their heads. Yes. Okay, so let's let me describe maybe a couple of, right, and then so yeah, so we have a singular fiber of type I2. So this is the generic fiber. So it has m-dimensional polynomial representation, m-dimensional representation, which is the factor of polynomial representation by this ideal. Okay, and it corresponds to a certain brane. And we can sort of play this game for all of them, right? So let me not bore you with all the details. So the singular fiber of type I2, when you had 3 singularities where the fiber was like 2 p1s with 2 double points. Here again, you can compute this. You have some polynomial representations, and now this finite dimensional module is a factor of polynomial representation over this Magdalene polynomial.
So just making sure. So this corresponds to alpha, beta, gamma, all these generic.
No, not okay. Let me show you the table. So in the table, so okay, so generic, yeah. So here alpha, beta, gamma are so here they're all 0, right? So the no, never mind. So yeah, here there is generic. Q is root of unity, and we have this generic fiber, right? And then the other guys, which correspond sort of to this picture, you have well, UN is this brane that corresponds to the Bungie with 2 exceptional divisors, right? It's even root of unity, and then this quantization condition, and then the Bungie itself comes from. So there are conditions which are not roots of unity, which is sort of maybe people haven't seen this before, but here it's kind of manifests itself. So if this condition is satisfied, then alpha and gamma are quantized like this together, right? Where k is the dimension +1, right? And each exceptional divisor comes from this condition. L is an integer, and gamma and alpha again quantized in this way. Yeah. So these are, if you like, right column is the condition on the existence of a Lagrangian brane. Middle column is the shortening condition representation category, and left-hand side is just the name of those representations from Cherednik's book. Okay, here's some horrible picture, but it kind of shows you the complexity of the whole story. So like, I think this is only drawn for h bar being real. So like if you in origin alpha beta gamma equals 0, have a singular fiber, and then as you go, as you change alpha, you kind of get this picture. As you go at a generic point, you get a generic fiber, and then at those 3 singularities, you get the 2p1s with two double points. But again, as you change the phase of h bar, it all kind of changes. So it's more complicated. Yes. No, this is like a modular parameter space of. So no. Yeah, that's right. Yeah. So like I try to draw the, and in fact, since alpha, beta, gamma can be complex, it's only the real slice of that. So.
And the phase vector R doesn't look like just actually, if I thought of this model, this is 3 different singular fibers at those.
Yeah, that's right. Okay, now let's talk about homes, right? So, well, you can compute those. So, on the well, you know, in the Hecke category, you have this home space is, you know, given by the Floer complex, right? Which is, you know, whose generators are differentials and they're defined by those intersection points. So, and on the representation side, you would, you know, see what happens. Like you could study extensions, like you have a module which can be extended by another module. So it turns out that if you impose several conditions at once, right, then some other interesting things may happen. So look, for example, this green brane U1, it has V and then two exceptional divisors. So if you impose simultaneously this condition and this condition, what you can show that sort of these two guys, they will decouple, right? So like the bound states will break, it will break apart, and then you have these two exact sequences. So okay, this is generic fiber, yeah, that's right. So think about it this way. So you are at the generic fiber position, and then you kind of approach this singularity where two conditions are satisfied at the same time, right? And then you'll get that you'll have basically two submodules, this U2 and U1, and then there is another which is not equivalent. So not equivalent, but sort of which obtained by applying this nonlinear involution iota, when U1 is a submodule and U2 is a factor module. So these two branes, they have the same support, but they're different objects in the Hecke category.
Because you have a superscript 1, 2, they like correspond to supported on different dynamics.
Yeah, that's right. 1, 2 even for the branes, right? So for yes. You're saying
your brain becomes reducible or what?
It's yeah. I mean, no, not direct. It doesn't split. It decomposes, right? So it doesn't. It's not a direct sum, but you know, it's you have exact sequence.
I mean,
so they don't.
In the A model, nothing special happens. What are you varying? So you say.
So now I want to impose two Lagrangian conditions at the same time, right? So my brane approaches the singular locus, right, where two shortening conditions, two Lagrangian conditions are satisfied simultaneously. Or you mean you change your alpha, beta, gamma, and you change your Q and T such a way that, say, this and this are satisfied altogether, right? So like, so basically, say two of the conditions are satisfied at the same time, right? So then you expect something else to happen. Like, so what happens in this picture? You have, well, then so the claim is that they never split into a direct sum, but you get a short exact sequence. Like you get some sub module and a factor module.
I mean, in the A model, you don't get short exact sequences at a point of moduli, some funny locus. It doesn't happen.
With some higher codimension locus, right? It's not just one. It's really like kind of have two different singularities colliding together. Yeah. So and then representation theoretically, you can see that to see how this sort of modules are different, you look at the X, so take the basis where Y is a diagonal matrix and see how X acts, right? And then turns out that the action is different. Like this matrix is the same, but like the star, which is a certain function of Q and T appears different.
Are you writing stuff on representation here, or you have a geometric?
So geometric was here. Yeah, so you can, so because there's this, yeah, so we claim.
What is this in terms of A-branes?
So there are two A-branes with the same support, but they have different lift, like different grading, different grade lift. Which we think is at least this is what we think. So like, and then the kind of you have two different short exact sequences. And they're different because, well, I mean, they're different geometrically and also different algebraically. Okay, and then similar game works with the nil cones. You have I0 star again. If you impose two conditions at the same time, say this one and this one, then we get this exact sequence. So U1, which is this green brane. So we have a sub, there's a iota. Again, there's an exact sequence like this, which on the representation side would correspond to having a sub module and a factor module. Yeah. No, so there's. Yeah, so we want to say that we expect that. Yeah, so like there's there's a. So we want to say that there's this home between. So there's like one home, right? So between say this brane and that brane, right? Which is this one. So I mean, on the Fokai side, you can compute the representation intersection numbers, right? So like the so we didn't compute the grading, but we just basically from what it appears to be, it's the same, the different A-branes, right? But they have the same support, but they have different lift. Yeah, and then we can end with this one. So we have the so all the representations, say from Cherednik's book or from this representation literature, there are factors of the polynomial representation module some ideal, right? But turns out that we have found the new ones, right? So if you take a brane, which is sort of shown here, right, with the green, right? So have a I, which is a subset of 1, 2, 3, 4. If and if this I has cardinality 3, so have a band G with 3 exceptional divisors, then you can have short exact sequence like this, right? And the corresponding representation N3, right, for I is equal to 3, is not going to be anymore the factor of the polynomial representation. So it's a reducible but indecomposable representation of DAHA, which well, was not known before. Yeah, so in principle, we can have any. So I can be any cardinality. Any of those 4 sets of 4 exceptional divisors can be attached to the big one, right? And then there is a.
So the brane you think you're describing is the guy you call N?
Yes. So N is the N is the brane. Yeah. So its support is shown.
Yeah. So I think what you want to say is that there's the N, that's the complex that where the B guy has the other guy.
Yeah, that's right. So
those guys would look like really connected sums. You would not write that.
Yeah, so I'm okay, sorry. So sorry, yeah, oh yes, so this is sequence of modules, right? And we want to say that yes, so this corresponding brane is lives here, right, in this complex. Is that what we're saying? No, so like, so Bn, this brane is part of home 1 from basically from collection of these guys. So if they have, so this sequence of modules corresponds to chain complex, right?
I think what you want to say is that your brane and is doesn't live in that home, but together you turn on an element of that home.
Well, that's,
yeah, that home.
But that's the same thing. Right?
It's not the same thing. It's not the same thing at all. I mean, one is a space, the other one is an object in character.
Yeah, but it's one home, right? So it's already.
No, it would just tell you what the grading is of
okay, I was thinking.
The string with expectation value you turn on that brane.
Yeah, perhaps right. So the
You wouldn't say that you're like, they go to that picture, you want to say, okay, I get my brain by turning on all the strengths at intersections between you.
yeah, over here, here, and here. Yes. Yeah.
That's what you want to say. But that you say it different. You don't say it the way you say it.
Okay, you can tell me right there. Anyhow, so yeah, you can so kind of that finalizes the match, and then yeah, so I can either stop here or I can show again maybe the statement, right? So maybe I can say, oh yeah, let's not go into Coulomb branch. So let me flash up the main statement again, and we can finish here.
So you have a picture where you have this W.
Which one?
You had a picture where you have this blue W.
Oh, I just yeah. So it's certain relation in the homology. It's like basically there's the. I mean, it's like it's certain like yeah. It's like you can basically you can try to understand topologically what happens, how this how this thing splits as it goes
So
to.
what do you say about this W?
I don't think there's anything. Yeah, I don't think there's anything particularly. At least I don't remember. Yeah. Anyhow, I think I should stop here. Yeah, thank you.
All the representations of spherical DAHA?
So we found all finite. So we found finite dimensional. Well, not all by any means. Yes, so we found irreducible finite dimensional, and then some reducible, which are indecomposable, but also finite dimensional.
Okay. Do you say all finite-dimensional?
But when you can keep extending, right? So it's like, in sense, like we find the core ones, right? So,
and is there like some reason why we should expect finite-dimensional representations to correspond to compactness? Why should those be?
well, yes, I was hoping to kind of this, well, so when we're quantizing space, right? So essentially, so think of it that there's some symmetry acting on it, right? And then like you would have, okay, so let's get back to the beginning of the talk, right? So in oscillator, we have a Lagrangian disk, and its volume gives you the energy level, right? So here's the same idea. We have a Lagrangian brane, which is supported with some Lagrangian cycle, and we expect that its volume, its eclectic sense, will be equal to the dimension of that representation.
Okay,
because there's an algebra acting on it, right? So you can, there's algebra which changes you the dimension, right? You can have from one polynomial to go to the next one, to the next one, to the next one, and then it corresponds to kind of blowing up your space by some fixed amount.
So in the one example you did, it ended up being that there was a dimension of space of line levels over.
Yeah, sorry, it's a space of section.
Is that a generic case of all of these are dimension of the spaces with the.
Yeah, that's the prescription. Yeah, so yeah, so then that formula should give you the dimension. It should give you, if you impose W cubic condition on the Planck's, it should give you the dimension of that representation.
Question. So how, so you're saying with some choice of parameter alpha, beta, gamma, say r equals 0, you get a singular. So, beta, you have some picture. Not this one, it's the picture with 3 axes of beta, gamma.
Oh yeah. It's a curtain, but it's not very precise. It just shows you what happens one of, yeah.
Yeah, that's right.
Okay.
So when you are on when you keep beta gamma equals 0, turning on alpha, it's like you turn on the size of the 3 little
four exceptional devices.
Right. And then if you move into the face, so you move into the face.
Yeah, then it's not true anymore. So basically, so it's not claim is that you can have this D4 diagram somewhere else if you turn on the face.
Turn on this, turn on 2 parameters like alpha, beta, not equal to 0, and beta and the gamma still equal to 0. So in that case, it's 2 banana. Is there a way to geometrically see the definition? How do I turn that picture is somehow automatically?
I mean, how to visualize it? Kind of.
Yeah, right. You can visualize something goes from 0 size to finite size, go from origin to this.
Yeah, I'm sure you need to lose the genus somehow, right? So it's yeah, I'm not sure. It's like I don't know this very well, so it's just yeah, I mean, you just look at the classification and you identify. So.
Okay, another question. So you go from this genetic place where I have this smooth fibers, torus, and I go to this
here.
Yeah.
Then you have it pinches, right? Then that part is easy.
And what if I go to the other axis? Should I still get similar pictures?
Axis.
For example, I keep alpha, beta. I keep 2 guys to 0. I turn on gamma. Would I get like a symmetric picture?
No. So I mean, then alpha, beta, gamma are not symmetric, right? So alpha is in A, right? And beta is in, I mean, the different parts of the kitchen.
So can you tell us again that this picture with a sphere with 4 guys attached? Where does it live? For which value of parameters? You say not only for beta and gamma it's 0, but also somewhere else.
So if H bar is real, then beta gamma is equal to 0, and alpha corresponds to T, the volume of those exceptional devices.
If H bar is
Real.
Okay.
So it's be a brane, and it's a so alpha gives you is related to the volume of those exceptional devices.
So a parameter Q was e to the alpha something, right? Alpha plus I beta.
T was in the T is alpha plus gamma. T e to the this one. And then I mean it's kind of mixed. This is a
That's the same T as.
No. So there's a T tilde that has Q in it. Yeah, so it's a bit more complicated. So I mean that cartoon, that picture is it's for certain phase of Q. It only works for like Q is real. So don't take that picture too seriously. It's just a cartoon of what in principle may happen.
So for example, this guy with the brane stuff at anyway, you say it exists. Can you just understand? You exist. It exists at some locus where 2 guys intersect.
Yes. Let's look at those. Okay, very good. So the table here. So it says it has to be this one and this one. So these conditions must be satisfied simultaneously. But they're both conditions on alpha and gamma. So it's the second part, right? When this kind of cone splits. I can show you some details in the paper after this. Yeah, kind of.
Other questions? Okay, that's thanks here again. We will have